All right, guys, so this morning we're going to take a look at what we call electric potential energy due to point charges dropped in space, right? Um, so we want to talk about we saw yesterday, um, if we have 2 point charges, there's a force between them. That's what this is here, right? Down here. We saw this. This is Coulomb's law. And what we could see is if I had a Q1, let's say, and we had a smaller charge Q2 over here, Q1, right? Well, firstly, too, there should be there's a radius between them, or distance, right? Q1, we could say, is fixed, right? In space, we've dropped it in space. And in the vicinity of Q1, we have potential energy, right? Which varies depending on how close you are to the fixed charge. Okay, so Q2 is experiencing some potential energy based on the presence of Q1, right? So what is potential energy? Potential energy is the potential to do work, right? And we can store it, and then we can release it in the form of work, okay? And so Coulomb's law varied based on R squared, right? Whereas the electric potential, how much potential energy Q2 would be experiencing based on the presence of Q1, only varies by a factor of R. It's inversely proportional to the radius, right? As opposed to the being inversely proportional to the R squared value, the radius squared value, right? So the electric potential energy could be positive or negative depending on the charges that are involved, right? So if the charges have the same sign, E is positive, right? Like charges repel each other, and so positive work must be done on the system to bring the two charges near one another, right? It'd be like, if you guys think back to when we did the work, the employee in the store who was pushing the buggy around and ultimately lifted a case of Coke from the floor upwards, right? Well, gravity was the force that was acting downward, right? And the employee had to apply a force in the opposite direction of gravity, and so positive work was being done. So if we think about 2 positive point charges, right, they're going to want to repel each other, right? Or repel, or at least Q1 is going to be fixed, but Q2 is going to want to repel, right? And so in order to move or decrease the radius value, we're going to have to apply a force in this direction, and therefore positive work must be done for 2 positive point charges, right? Or 2 negatives as well, right? It's if they have the same sign, same charge, but same sign on the charge. If they're both positive or both negative. Okay. The opposite is true if the signs are opposite, right? The potential is going to be negative, right? And that's because now the point charge Q2 wants to actually it's attracted to Q1, right? So for us to move it closer, that would be like when the customer came along in the store and took the case of pop from the shelf and put it into her grocery cart, right? The force of gravity and the force of gravity was pulling the case of pop from the shelf down to the cart, right? And so it's not as if the customer was doing as much work as the employee lifting it up, right? But it's definitely, it was acting in the opposite direction, right? The magnitude of the force that the customer had to apply was much less than the force of gravity, and so negative work was done in that instance, right? Same thing here, right? If we have an attractive force between those 2 point charges, negative work must get done in order to move or decrease the radius, right? Because they're attracted to one another. Okay, and so these graphs here depict what the electric potential looks like, or the graph, as it decreases, almost looks exponentially, right? As we increase the radius, right? And that's between 2-point charges, okay? So overall, as we increase the radius, right, the electric potential energy goes towards zero, or approaches zero, okay? So electric potential, okay, just represents the amount of work, I'm just down here in this paragraph now, it represents the amount of work necessary to move a unit positive test charge from a rest at infinity to rest at any specific point in the field of Q1, right? So that just means we're going to place a charge Q1 somewhere in space, right? And it's fixed. We're going to fix it in one location. And the electric potential is how much work you would have to do, right, to bring a second point charge, Q2, into proximity of Q1, right? Because Q1 has a, let's say it's positive, right? You guys saw how the field lines looked for a positive point charge. That would have been a grade 11 thing, right? And so you know the positive point charges are pointing outward, right? So we're influencing this electric potential field, right, based on the presence of Q1, right? And so if I were to bring Q2 closer, depending on its positive or negative, work is going to need to be done. It could be negative work, it could be positive work, right? The electric potential is measuring that amount of work. Okay, so we come down here. There's two key distinctions that I just want to bring to your attention here, okay? Electric potential energy is associated with the charge, okay? Only particles can have energy. Electric potential is associated with a potential or a position in space, okay? Okay, I'm just going to pause here for a second, just to let everybody kind of regroup here. Okay, a lot of this is text that I've kind of extracted into a nice kind of compiled note for you. Okay, EE again. This should maybe even be like a little e. Sorry, not capital E. So electric potential is the energy a charge has when it's placed in a field. Okay, we discussed that up above. Q is the charge that is actually placed in the field, and V is the electric potential of the field created by the point charge. Okay, and point charges are tricky because their field strength varies as you move away or towards them, right? So it's only really like we can do these calculations if we're not if we kind of fix the point charge relative to the other one, right? We know how far away it is. If we start, it's very difficult to measure the electric potential if we're changing the radius inward, right? That's calculus, right? How something changes with time. Okay. So anyway, I'm going to leave some of this. I thought most of the harder stuff today would be like, could I show you some calculations, and you guys you have the textbook there for reference, and some of the Khan Academy videos will do a good job at teaching this all to you as well. I just wanted to get you exposed to some of these equations and maybe where you could apply them, right? This one here is the electric potential difference, or the change in voltage, okay? And you know, we could use these equations, you know, to find, okay, well, what's the potential difference between one spot and another, right? The change in voltage, right? And down here, it's just an equation, right? So it's delta V is the change in electric potential of the field, right? Delta EE is the change in electric potential, energy of the field, right? Q is the charge in the object. E is the electric field intensity, okay? And we're actually we're feeling a force here now, right? Because we're seeing a Newton, just in the units, we're seeing a Newton per coulomb. We're seeing it's almost like a force, right? And delta D is the displacement. Okay, so we can use this equation, and we'll see it in context down here a little bit, okay, as to where we could use it. Okay, so we just want to calculate the electric potential at a distance of 0.4 meters from a spherical point charge of positive 6.4 times 10 to the negative 6 coulombs. Okay, so what are we going to use? Well, we could use the equation that says, okay, well, I'm looking for the electric potential. What is the electric potential? It's V. And sometimes when I do these questions, just to, I mean, we're not, I like to denote the potential with kind of just different from like something that might look like a velocity, right? And so we can see the potential is KQ over R. Okay, we just plug in our information, right? We know what K is. It's 9.0 times 10 to the 9 times the point charge that we placed in the field, 6.4 times 10 to the negative 6, and divide that by how far are we from the point charge? 0.4. Because this one's not even squared, right? You should see 1.4 times 10 to the 6 volts, right? And remember what this is. This is, I'm just going to do a little like writing here. It's the amount of work per unit of charge, and I'll go back and show you where that comes from. Per unit of charge required to move the charge from infinity to 0.4 meters. Okay, so it's saying here, the last part here in the question, we're taking that the potential energy is going to be 0 at infinity, right? We talked about that above. As we increase R, as R approaches infinity, the potential energy goes towards 0, right? And so what we're saying is we're starting from that infinity point and we're bringing it inward towards the point charge, right? This is the amount of work needed, right? Another way to write the volt or potential energy is joules per coulomb. So it's the amount of work needed, right, per unit of charge, right? Okay. So let's take a look at number 2 here. And what we're going to do, I'm just going to show you how to apply some of these equations, right, based on the scenario, right? So how much work must be done in order to increase the potential energy of a charge of 3.0 times 10 to the negative 7 coulombs by 120 volts? Well, we'll see delta V, the change in voltage, would be equal to the work divided by Q. Okay, and then so work, the thing we're looking for, would be equal to Q delta V. You know the point charge, you know the change in voltage, you just plug them in. So 3.0 times 10 to the negative 7 times the change in voltage, 120. What do you get? You get work equals 3.6 times 10 to the negative 5 joules, right? We measure work in joules. Okay. If I come down here, in a uniform electric field, the potential difference between 2 points, 12 centimeters apart, is 1.5 times 10 to the 2 volts. Calculate the magnitude of the electric field strength. Okay, so this would be like if we were to place another object between the two of these. Okay, so we have two potential, like 2 points, right? And we want to find what's the electric field strength in that, right? So we're almost looking for like a force, right? Like what are you going to experience when you actually place yourself at that particular, like in the middle, 12 centimeters, right? Or I suppose at 12 centimeters, right? So we're going to say, okay, well, the change in voltage is equal to the field strength multiplied by delta D, right? Okay, so you just plug in, okay, well, delta V we know is being 1.5 times 10 to the 2. All right, we gotta remember this is in centimeters, gotta work in meters, so we switched it to meters. Right, and the field strength is gonna equal 1.5 times 10 to the 2 divided by 0.12, and the field strength is okay. Okay, again, this is like the Khan Academy is going to supplement this lesson, right? This is just like, how do we use these equations and where do we, like, what does a question typically look like and how do we extract this information, right? And put it into the equations, right? So the magnitude of for the last one, the magnitude of the electric field strength between two parallel plates, right? So we're talking about, you know, if you were to go, parallel plates would be something like this, right? They'd have charges. It could be all positive. And negative, right? Could be positive, right? When you were to place an object in the middle of these two things, they're going to experience some force per charge, right? Or if you were to place a point charge in the middle of those two things, right? There's kind of a, depending on the charge that you put in there, you're going to feel a different kind of force, right? So we want to find what is that force based on the information in the question. Well, the electric field strength between two parallel plates is 450 newtons per coulomb. So we know, I'm just going to move this out of the way. We know the field strength, okay, and the plates are connected to a battery with an electric potential, so we also know the potential difference between these two, right, is delta V. What is it we're looking for? Well, what is the plate separation? How far apart are these two things? R. Right? Saying, okay, well, R is equal to unknown, or delta D, right? Could even call it delta D. Right, and we know delta D is equal to the change in voltage divided by epsilon, the field strength, right? Which is going to equal 95 divided by the 450. Okay. So hopefully these help. I mean, it really comes down to like, this is a very tricky concept from the standpoint of keeping track of potential energy or like electric potential energy and forces and wrapping your head around the fact that like when we drop a point charge into space, it influences the close proximity, right, based on its charge. Okay, that's what some of these equations are doing for you. They're figuring out the magnitude of how it's going to affect something as it's brought into that field. Okay, so I've posted 2 textbook sections. Okay, and I'll put some Khan Academy videos up as well. And hopefully these solutions help with these questions down below. Okay, and if you have any questions, feel free to ask. Happy to help. Okay.